Multivariable ordinal regression offers a lot of valuable insights if you know how to extract them from the model. Unfortunately, most tutorials stop at a basic model summary, missing out on deeper opportunities. In this video, we'll learn how to select the best predictors for an ordinal model, visualize predicted probabilities for each level of the ordinal outcome at any predictor values you choose, compare those probabilities using absolute risk differences and risk ratios, extract and compare cumulative and exceedance probabilities, and much more. We'll use the free wage dataset from the ISLR package. To make things more intuitive, we'll simplify the target variable education into 3 ordered categories: high school, college, and university. We'll also clean up the job class predictor, renaming it to IT versus not IT, and focus on a single year to streamline our analysis. To fit the ordinal regression, we'll use the cumulative link model function from the ordinal package. The model formula consists of 2 parts. On the left side of the tilde, we place our ordinal outcome with 3 education levels. And on the right side, we include our predictors. And dealing with a large number of predictors can pose significant challenges. One issue is redundancy, where predictors convey similar information, a phenomenon known as multicollinearity in statistical terms. To assess this, we can use the intuitive check collinearity function from the performance package. Since moderate correlation and a variation inflation factor below 10 are acceptable, we can confirm that our model has no multicollinearity issues. However, having many predictors raises another concern: overfitting. This occurs when you have more predictors than observations, leading to horrible model performance. To address this, we need to eliminate less important predictors, and there are 2 effective methods to do so. First, we can use the ANOVA function from the CAR package, which provides chi-squared effect sizes and p-values to assess predictor significance. In our model, wage and job emerge as most important. I use the term important deliberately because with effect sizes we can create visualizations similar to the variable importance plots seen in random forests or other machine learning models. The second method is even more powerful because it involves the GL-multi algorithm. This approach generates models with all possible predictor combinations, offering a far more robust solution than simplistic backwards selection. By using the plot command with the type as argument, we can visualize the relative importance of predictors across all models. A predictor's importance is calculated as the sum of the weights of the models in which it appears. Predictors that frequently appear in high-weighted models receive higher importance scores. A vertical line at 80% indicates that predictors to its right are included in 80% of the models, often serving as a cutoff to distinguish highly important variables from less critical ones. In fact, the GL-multi algorithm is so valuable that I've created a separate video on it, and I use it in my scientific research all the time. Now, let's refit our model using only the 2 key predictors, wage and job, as both GL-multi and CARS-ANOVA confirm their importance with clear, interpretable metrics. To evaluate our model's performance, we can use the intuitive performance function, which provides key metrics like Akake's information criteria, Bayesian information criteria, R-squared, and more, depending on the model type. Additionally, the effect size package helps us to interpret these metrics. For instance, we can analyze the coefficient of determination R-squared, which indicates how well our model fits the data. In our case, an R-squared of 0.299 means our 2 predictors explain nearly 30% of the variance in education, suggesting a substantially good model. The interpret R-squared function even provides a reference to a paper for deeper insights, which you can explore if interested. Oh, and by the way, while you can build an ordinal model in R using at least 5 other functions, they all suck in some aspect of model interpretation. To save you time, I recommend sticking with the CLM function from the Ordinal package. However, one alternative worth mentioning is the polar function from the Mass package, which stands for Proportional Odds Logistic Regression, another term for ordinal model. This brings us to the critical proportional odds assumption, which we must verify to ensure our model is truly ordinal. Why check it? Well, because failing to check the model assumptions is like diving into a pool on a hot day without confirming there is water in it. To test the proportional odds assumption, you can use the Brunt test from the GoFCut package, a significant omnibus p-value, where omnibus simply means the general p-value for the entire model, indicates a violation of this assumption. However, a more reliable method is visualization using the plot xmin ordinally function from the RMS package. This graph displays a solid line representing the actual mean salary of the predictor across the ordered outcome categories and a dashed line showing the expected predictor values if the proportional odds assumption holds. When the solid and dashed lines align closely, as they do for both predictors in our example, the assumption is satisfied and our model is solid. If the lines diverge, the graphical method outperforms the Brunt test by revealing the extent of this violation. This insight helps us determine whether the ordinal model is appropriate or if we need an alternative approach, like multinomial model or similar. After fitting our ordinal regression model, we need to interpret the results. Our model shows that higher wages slightly increase the likelihood of being in a high education level, while having a non-IT job decreases this likelihood compared to an IT job. Since our proportional odds assumption holds, the effects of wage and job class remain consistent across all education thresholds. So we could actually stop the interpretation here. And that's what most tutorials do. They only use the summary function and interpret a single number. However, our model offers far more valuable insights, and we're just getting started. By using the powerful Emins package, we can dive much deeper than a basic summary. This package enables us to extract 95% confidence intervals, probabilities for individual education levels, and cumulative probabilities for education thresholds. It also allows us to perform post-hoc tests to compare these levels using risk differences or risk ratios. So let's explore all the insights our model can provide step by step. To ensure the Emins package delivers reliable results, we can use its Emins and mtrans functions to obtain the same log odds estimates as the summary function, along with 95% confidence intervals and basic contrasts or post-hoc tests. Next, we can generate a reference grid from our fitted model to examine all multivariate response levels of education: high school, college, and university. For clarity, multivariate refers to multiple outcomes, while multivariable refers to multiple predictors. The reference grid also shows the predictor values at which the probabilities of these education levels are calculated. To visualize these predicted probabilities, we'll use the MIP function with the mod argument set to probability. By default, this function calculates probabilities at the average wage of 111,000, which is kind of limited and boring. To get a clearer and more exciting picture, we can tell the MIP function to calculate probabilities using a range of wage values we choose. This makes the result for the wage predictor much more interesting, while keeping the effect of job type on education fixed at the average wage of 111,000. And that's a key feature of a multivariable model. It shows how one factor affects the outcome while keeping everything else constant. But here is the exciting part. We don't have to fix the effect of job type at just the average wage of $111,000. The emip function lets us choose different values for other predictors to see how they influence the results. Let me show you how this works and you'll love it. Since we have two jobs, IT and non-IT, we can easily show the probabilities for different wages for each job by adding a vertical bar and the word job to our emip code. Plus, we can calculate the probabilities of education levels for different jobs at specific wage values we pick, not just the average. For example, we can look at $50,000 for lower income folks, $150,000 for the middle class, and $250,000 for higher earners to see how likely they are to have a certain education level. Since we've shown how both predictors behave in terms of each other, the two sets of graphs we created shared very similar information. This extra effort was worth it though, because the more detailed graph on the left reveals that the highest chance of having an IT college degree peaks at around $140,000, while the peak for an engineering college degree is around $160,000. Now, since we have so much repeating code, we can bundle it into a simple, elegant function that creates clean emip plots without the hassle. You can just screenshot this function and ask ChatGPT to type it out for you for free, or if you want the full R code with explanations for any of my videos, join the channel at the coffee level or higher. Our create emip plot function lets us focus on what matters without all the extra clutter. Specifically, it takes the model formula to specify what we want to visualize, the mode to choose the type of probability we need, and a list of predictor values to see predictions for. But here is the most exciting part. With these estimates and their error bars for the predictor values we pick, we can compare any of them to each other. The first predictor listed after the tilde in our formula is the one we use to compare its categories. For example, by adding pairwise before the tilde, we tell the immense function to compare the categories of that first predictor. If we are working with a numeric predictor like wage, we need to choose specific wage values to compare. But for a categorical predictor like job type, we just put it first after the tilde. No extra work needed. The immense function gives us two main results. First, it shows the probabilities based on our chosen mode. Selecting prob gives us the basic probabilities for each education level, while cum-prob gives us cumulative probabilities, which we'll cover later. Second, it provides contrasts, which is just a fancy way of saying the differences between those probabilities. By default, it calculates absolute risk differences by subtracting one probability from another. However, we can also calculate risk ratios, which show relative differences by dividing one probability by another. I explained risk ratios and how they relate to odds ratios in more detail in my first Ordinal Regression video, so check that out for the code and a deeper dive into the topic. This output gives us everything we need, but it can include some extra clutter like standard errors, degrees of freedom, and z-ratios we don't always want. Plus, it's not in the clean, tidy format we often need for publications. To fix this, I created a custom function that delivers neat, publication-ready results. All you need to do is tell the function what you want to display: probabilities, risk differences, or risk ratios. For example, using our early comparison of different wages, we can start by asking for probabilities. This gives us a clear, good-looking table with probabilities and 95% confidence intervals for every combination of wage, job type, and education level. Next, we can calculate absolute risk differences between wages, including 95% confidence intervals and p-values to check if the differences are significant. For instance, a non-significant p-value for non-IT college graduates tells us they have a similarly low probability of earning 50,000 or 250,000. If you prefer risk ratios over risk differences, just ask for it. I explored every possible combination with this function and loved how convenient and useful it is. And if you found this video useful, please give it a like or leave a comment. It really helps the channel grow. By the way, don't be surprised if p-values differ slightly between risk differences and risk ratios. They are based on different tests, which is totally normal. I covered this in detail in another video. I also already explained why risk ratios are much more intuitive to understand than odds ratios. That's why I do not calculate odds ratios for ordinal model here. Here is something cool. If we use our response variable education as a predictor and place it first after the tilde, we can compare the probabilities of different education levels against each other. Most results are clearly significant, but let's intentionally focus on a non-significant one because it stands out. For instance, the probability of earning 150,000 with just a high school degree in a non-IT job is about 25%, while the probability of earning the same 150k with a university degree is even lower at around 14%. The absolute difference of 11% between them is so small it's not statistically significant, and the risk ratio of 1.8 shows having a high school degree is only 1.8 times more likely than a university degree, which is also too small to be significant. Finally, to compare job types for every combination of education and salary, just place the job predictor first after the tilde. In my previous video, I explained that cumulative probability is the chance of achieving an education level at or below a certain point. It's like cutting between education levels. By setting the mode to linear in our model's reference grade, we can explore these cut points. For example, at the cut point college-university, we are looking at the likelihood of having a college degree or lower, which includes high school. Note that we don't display the cumulative probability for rating less than or equal to university, as this would always equal to 100%, making it redundant. To visualize these cumulative probabilities, we just need to tweak our createMePlot function by changing the mode to cumProb instead of prob. For this example, let's keep using job in the first plot and use only two wage values in the second plot to show how flexible the means package is and how we can choose exactly what results we want to see. On these plots display the cumulative probabilities of education levels based on wage and job type. The two curves represent different education thresholds. The red curve shows the chance of having a high school degree or less. As wages increase, this probability drops sharply, hitting near zero around 200,000, which makes sense. People with only a high school degree are unlikely to earn such a high salary. The blue curve shows the chance of having a college degree or less. At high wages, this probability stays above 50%. What's cool about these cut points is that the immense package treats them as a synthetic predictor called cut, even though it wasn't part of our original model formula. By setting the mode to cumProb, we get cumulative probabilities for these cut points, along with their absolute risk differences, which are risk differences, and relative differences, which are risk ratios. For example, the probability of earning 250,000 in an IT job with a college degree or less is only 17.5%, which makes sense since you typically need a university degree or even a PhD to earn such a high salary. The tables showing both absolute and relative differences between wages, education thresholds, and job types are significant and provide clear effect sizes you can easily include in your reports. Finally, exceedance probability is the chance of reaching an education level above a certain point. For example, at the college-university threshold, it's the likelihood of having a university degree or a PhD rather than a college degree or lower. To create plots, calculate exceedance probabilities, and compare their differences using our earlier code, we just need to switch the mode from CumProb to XProb. For instance, the chance of earning only 50,000 with an IT degree higher than college, like a university degree or PhD, is just 3%. So it's very unlikely to struggle that much in your career. Even earning 150,000 seems unlikely with a probability of about 28%. But earning 250? That's much more likely, with an 83% chance. This shows how much education can matter. And if you have watched my 3 previous videos on ordinal models, you are already highly educated in the topic of ordinal regression. But if you have just stumbled on this video, I highly recommend checking out those earlier videos to get a solid understanding of the theory and our techniques to get the most out of your ordinal models. Hey guys, that's the real me. Just so you know, the person behind the screen is actually a person. I'm Yury Zablotski, a scientist and biostatistician at the University of Munich. I'm not an AI, I'm a real person making this content for you. I don't show my face often since it doesn't bring any statistical value to the video, but if you prefer to have some personal touch in the age of AI and would feel more connected seeing me talk from time to time, let me know in the comments below. Your experience here is my top priority. So thanks for watching. Thanks for your continuous support. I love you all.